Welcome all to the next episode of the YugabyteDB Friday Tech Talks. It's my pleasure to welcome you all. I'm Kannan, one of the co-founders at Yugabyte, and I have with me here one of the very early engineers at Yugabyte, Rahul Desirazu, with a very interesting topic that I think you'll find quite useful. So with that, Rahul, why don't you take it away? It would be great, maybe perhaps if you can start by introducing yourself, maybe share with people some of the things that you've worked on at Yugabyte, and then we can get into the topic of the talk.
So my name is Rahul. Thanks, Kannan. I've been at Yugabyte for almost 5 years now, and I'm on the DST, or Distributed Storage and Transactions team. In terms of some of my past projects, I've kind of worked on the encryption space, read replicas, and various projects in the kind of control plane and load balancer, as well as cross-cluster. So let me just share my screen. So let me give a brief kind of intro of kind of what cross-cluster is and kind of the motivation for building it. So at its core, cross-cluster is when we have a source universe and a target universe, and any write that comes to the source is eventually replicated over to the target. So a pretty simple concept. But kind of why do we want to build this? Like, what was the motivation? So first, let's kind of imagine a use case where a user wants to be able to tolerate single region failures. So basically, in the case that a region goes down, another region kind of just takes over and can continue serving reads and writes. So for this case, kind of the simplest solution is to have a single cluster multi-region or multi-cloud setup. So imagine if all the leaders are in region 1 and region 1 goes down. Either region 2 or region 3 can pick up once it has all the leaders. So in this way, it can tolerate region failures. But now let's add the condition that we also don't want cross-region latency network hops. Now the solution no longer works because obviously any write that comes in will have to go through the raft consensus, and that will be a cross-region network hop. And that's kind of the core of what kind of drives cross-cluster, where we have these two regions. So in this case,
so maybe Rahul, just on the previous slide, just to emphasize. So I believe all three pictures that you're showing are single cluster deployment choices.
Yes.
The first picture seems to be just across zones in a region, but that's not region failure tolerant, correct? But the middle picture is a single cluster stretched across 3 regions. It's region failure tolerant, but has the trade-off that latencies would be higher because you're doing synchronous replication with raft consensus and so on in a multi-region manner.
Exactly. Yes.
Thank you.
Yeah. So yeah, I guess that's the kind of motivation for building cross-cluster, where we have region 1, region 2, and obviously the system can tolerate a region failure. But for any given write to a single cluster, it just goes through its own AZ. There's no kind of cross-region network hop. And all the cross-region traffic is asynchronous. So that's kind of the main kind of core use case for cross-cluster. There's a few additional use cases as well. One is kind of the active-active setup, where both clusters are taking their own independent writes and then kind of trading what they know every so often. And there's other topologies as well. So for example, a hub and spoke type model, where there's a bunch of like sensors or IoT sensors, and they're all kind of taking in data and writing to a central hub. And there's various triangle formations and daisy chains formations as well that users can do. Let's talk a little bit about the kind of high level objectives and functional requirements for cross-cluster. So first off, there's eventual read consistency on both sides. So what this means is that if all records have been replicated, any read on the source should match a read on the target. So that's kind of the first point. The second is last writer win semantics in active-active setups. So in the case that both clusters are writing to the same key, instead of kind of going through the transaction conflict resolution path, we just say that the write with the higher timestamp wins. And finally, we want low RPO and RTO. So what does this mean exactly? So for RPO, we can kind of almost think about this as the amount of data lost in the case of an outage. So obviously, let's say the lag is 500 milliseconds and the source region goes down and the target gets promoted, you've kind of lost those 500 milliseconds worth of data. So kind of minimizing this number is obviously an objective. And finally, RTO. So how long does it take for the new system to come up and running? And given that the target universe is just a Yugabyte cluster, it's as simple as kind of redirecting the client over from the source to the target and then just continuing to run the workload.
Rahul, if I could add a little bit of commentary around the requirements. So I think it's worth calling out that in the simplest incarnation, the use of this feature of cross cluster is to really take two independent clusters. Each one is horizontally scalable, elastic. It's a multi-zone cluster, but basically pairing these two clusters using this async replication mechanism, right? In the simplest incarnation, typically there will be a unidirectional pipe, right? Maybe like going from Yugabyte cluster 1 in region A to Yugabyte cluster 2 in region B, and it's unidirectional. And in that case, essentially, what we're talking about is on the target cluster, the reads are arriving asynchronously, but almost in near real time. So it's eventually consistent, but almost like near real time. And that also means like the way we are accomplishing the low RPU objective is that this async replication is near real time. So if the network is healthy, the target cluster will be caught up within a matter of seconds. Like usually the lag should be less than a second or so. Is that fair?
That's a super fair point. And yeah, in steady state, typically you'll see lags of under a second, and often it's near real time, as you said. The only time you kind of expect to see higher lags is in the case of an unhealthy network or network partition, and then lag can grow. But yeah, that's totally.
And also the last writer wins semantics is should not be a concern in unidirectional setup, but like you said, like active, or sometimes if you refer to it as bidirectionally set up, if this cross cluster is set up bidirectionally, where both clusters can independently receive writes, then it is important for users to understand that Yugabyte has a simplistic, like latest writer wins model, but this should not be an issue if on the two sides you're writing to different sets of keys or different partitions. But if you're writing to the same row, then yes, it is important to be aware of this restriction.
Yes, totally. This is just for the case where both clusters are taking their own independent writes. Yes.
Yeah.
Cool. Oh, and then let's talk about some of the user operations that to kind of control xCluster. So everything happens in the notion of replication groups. And a group is a kind of set of end tables or tables and indexes. And the user has the ability to kind of set up, delete, and alter replication on these tables and indexes. In addition, if a table already has existing data, the user can create a checkpoint on the source, do a backup restore of that table's data to the target, and then continue replication from that checkpoint. In addition, the user can pause and resume replication. And this is especially useful if the user is upgrading, where the best practice is to pause, upgrade, and then resume. And finally, we expose a lag metric. It's a per table kind of aggregate max across all tablets that shows the lag per table. And this is especially useful if there's a network partition where the user can kind of see the lag is continually increasing to know that there is something wrong with the setup. Cool. Let's move on to the architecture and kind of how we built this and maybe some of the lower level constructs. So everything happens, the polling happens at a per tablet level through a get changes API. And this get changes API takes a tablet and an op ID. So this op ID is kind of a raft level construct for actually determining where the user or the source is left off and how many records to get. And the source tablet uses its write ahead log to kind of serve replication requests. And this kind of naturally goes because the write ahead log has every single record written to the source. So we know we'll never lose any data when replicating it over. The thing is that WALs are garbage collected pretty aggressively, especially when we do a flush to RocksDB. So we retain WALs for 24 hours. Now what this means is that if there's a network partition for less than 24 hours, the user will be able to, the system should just heal on its own without any kind of user or manual intervention. And finally, we store a CDC state system table on the source side, which most notably kind of maps tablets to checkpoint op IDs. So I noted that the get changes request has an op ID that typically the target will pass in. But if there's been a rolling restart or the kind of stream just bootstrapped, the source will need to know where to leave off so that it can kind of start at the appropriate point. I'll have a demo to maybe go through this, but just I'll touch upon some of the replication steps. The first step is that the user runs the DDL on both sides. So the create table, they run on both the source and the target. Then they call setup universe replication on the target for those end tables or end tables and indexes. This will trigger a schema validation for all those tables. So the request will only go through if the schemas match for all the tables passed in, which makes sense because if the schemas don't match, then replication just won't work. And this will create the tablet mapping. So this is how the source knows which tablets, or the target knows which tablets to pull for. The mapping is of target tablets to source tablets. And the leader of the target tablet is responsible for pulling for the source tablet. And this is really nice because in the case of an outage where the leaders move over, as soon as the tablet has a new leader, we'll automatically just end up pulling for the source tablets. So it's a very highly available kind of architecture. And the number of shards don't need to match. So one cluster can be bigger than the other, or they can be splitting, and there can be 1 to n, n to 1 type sharding relationships. Using this, once the source side receives the pull, it gets all the records since the last op ID pulled for and returns them to the target. And finally, the target uses this to apply to its local RocksDB, and then continue the process by pulling for the new set of records. So at a high level, this is kind of the setup to happy case type flow. But there are various things that can kind of go wrong. So first, let's talk about transient failures on pull and apply. And this can be for various reasons. There can be a network outage. There can be a CPU bottleneck, a thread bottleneck. So we have various G flags for controlling the number of outstanding get changes requests, as well as for putting an idle in between applying locally and pulling for new records. And in addition, we also have an exponential backoff mechanism where if there is a partition, we don't just keep on pulling and we kind of back off till we're pulling maybe once a minute. We can also have planned or unplanned outages, either through data center outages or rolling restarts. And as I touched upon earlier, because we kind of tie polling to leadership, the system will continue to run as soon as the tablets on that kind of out DC kind of go to another server or data center. So in that way, we kind of remain highly available. And we have kind of 2 network partition cases. So for the less than 24-hour case, because we retain walls for 24 hours, the system should just be able to heal on its own with no user intervention. But if there's a longer than 24-hour partition, now the user needs to go through the bootstrap process I touched upon earlier, where they create a checkpoint, do a backup restore, and then start replication from that checkpoint. Now for some ongoing work. First thing is kind of automatic DDL replication. I mentioned in kind of the walkthrough that the user has to do DDLs on both sides, but we can imagine a case where the user already has replication set up on a table.
Maybe Rahul, one suggestion is maybe once we do the demo, if we can come back to this slide so people may have a little bit more context.
For sure, yes. Yeah, that's my slide. Let me share. Cool. So just for some context on this demo, I've already created 2 clusters. And on both these clusters, I've already created a table of foo, which is just a simple int primary key. So I can just kind of show what this means. So select star from foo. And this is just an empty table right now. And it's on both the source and the target side. So let's first start by setting up replication on this stream or on this cluster. So I'll just copy the command here and kind of go through what this means. So we're calling setup universe replication on the target universe, and we're passing in the producer cluster UID, the producer master addresses, and the producer table. And this can take in multiple tables and indexes.
Rahul, were you sharing a different terminal? Right now, I'm seeing the select star from foo terminal.
1 second. I'll just share my desktop then. Is this better? Can you see?
Yeah, now I can. Now I can see the YBadmin command. Yeah.
Perfect. Let me go through that again then. So we're calling the setup universe replication on the consumer master, we have the producer or the source UID, the source master addresses, and the source table. And this can take in multiple tables or indexes, but just for this demo, let's work on this one table. And let's wait for this to finish. Should take maybe about 5 to 10 seconds. Great, so replication was set up successfully. Let's kind of validate that this actually works. So we have a command called the CDC streams, and we can run this, and it should return the stream that we just set up. Yeah, so we just created a stream ID. It's on the table that we wanted. And we see that the state is active. So it's ready to kind of accept writes. So now let's insert some data into the source side. So let's insert a few values. So let's insert 0, 1, 2, 3, 4. And let's just ensure that those got written. Great, we see those. And now let's ensure that they've been written on the source side as well, or on the target side as well. Great. Yeah, so we see that they've been written on both sides. Cool. Yeah, that's about the demo. I can go back.
One question, Rahul, like if there are if the table has an index, then does the user have to set up the stream on the index separately too?
Yes. So right now, any kind of DDL needs to be done on both sides first. So if there's an existing table under replication, the user creates the index on both sides and then sets up replication on that newly created index.
So the index also has an ID, like a table ID, and just like you set up the replication stream on the main table, they would set it up on the index as well.
Exactly right. Yes. So you can treat the index like any other table.
Cool. Where you want to show how to look for the lag metrics and so on, or not covering that today?
So it's a bit, this is a local setup, and I think the lag metric is mostly kind of through our like a Prometheus or a platform. I can maybe just go to the tablet server level page and see what we have. So
yeah, we can show the internal metrics perhaps, and then of course there are like there's tooling built around it to consume it in an easier fashion.
Yes, so this is kind of our T server level metrics page, not the most readable, but we have a metric called async replication committed lag. And this is kind of the per table metric that I was talking about, as done as a max across all tablets. And we see right now, I can quickly kind of just go through what this means. So this is the stream ID, the table that we set it up on, yugabyte.foo. This is the time when the metric was collected, and this is the metric value. So we see that the metric value is 0, which is good because everything has been caught up. And this is a much more readable kind of metric through platform or through Prometheus.
Yeah. So Rahul, there's one question on the LinkedIn channel. Is there one replication stream per shard, or is it per table?
So setup is done per table. So the command that I ran was at the table level, but the actual polling, the internal polling API is done at the per tablet level.
And then the system handles the case that the number of, like I think you already called this out in an earlier slide, that whether the number of tablets on the source and target, even if they are mismatched or the source and target clusters are uneven in size, the system knows how to balance the work across these shards and pull the right sections and apply to the right regions in the target tables, right?
Exactly right, yeah. So either like both clusters are different sizes to start, or there could be splitting in between. So the system can handle both those cases.
And the other question might be a lead into the ongoing work slide that you had. So one of the questions was around how do you deal with schema changes or alter table commands, right? So perhaps you can cover that as part of talking about some of the ongoing work.
Sure thing. So right now, maybe I can touch upon schema changes. So In the case of a schema change, the kind of issue that we have now is that the user runs the alter on the source side. So now the source is taking in the writes under the new schema, but the target can still be under the old schema. And in this case, we might get a schema mismatch until the user has applied the same DDL on the target side. So kind of some of the ongoing work is to support automatic schema replication. So, given the user runs an alter on the source side, that's automatically replicated over to the target. So we never have cases where we're trying to write data from a new schema to an older schema. That's kind of one aspect of it. The other is kind of with indexes. So I kind of noted that right now the user has to create the index on both sides and set up replication. But it would be very convenient if we just set it up at the table that for any indexes created, we automatically replicate those newly created indexes. That'd be a lot less operationally intensive. So that's kind of another aspect of DDL, the DDL story that we're trying to create. I can also maybe touch upon some of the other ongoing work. So another is for atomic and ordered multi-shard transactions. So given that polling happens at a per tablet level, we can end up with the case right now where some tablets are further ahead than other tablets. So doing kind of a select star on the target side might yield like a jagged edge or inconsistent results. So we need some work to kind of have a coordinator which ensures that all tablets are kind of caught up to the same point before we do a read there. So that's kind of the story for atomic multi-shard transactions. But right now we have support for the single shard transaction case. And I think just a general thing we're doing is overall hardening for large setups or setups with low resource machines. Because the xCluster can be kind of operationally intensive or intensive when there are many tablets and tables. So anything to do to lower the number of threads or the lower CPU usage is always useful.
Thanks, Rahul. Maybe any other insights into what were some of the challenging aspects of this project?
Challenging aspect. I think, good question. I think one is definitely kind of maintaining the CDC state table. Imagine a case where there's many tablets and all of them are concurrently serving get changes requests. We really want to limit both the number of threads used on the source side so that it's not overloaded with just serving get changes traffic. And also, given that everyone is trying to write to the CDC state table, we needed some pretty intelligent batching to make sure that we're not always writing every time we update the checkpoint, and that we do like some kind of like an interval-based batching when we write and read from CDC state. And this involves, a caching mechanism on the source side so that we're not always reading and writing. We can just use the cache when we can to serve reads.
And how frequently do the consumers checkpoint their state in the CDC state table? I can imagine that you don't want to checkpoint after every read. That means you introduce a different bottleneck. Yes. So is it about once a second or something like that, or do you remember?
It's actually once every 15 seconds or so.
Once every 15 seconds. Got it.
So otherwise, everything is like an in-memory kind of tablet checkpoint map. And every 15 seconds, we kind of flush that to the CDC state.
And is this state table itself a distributed table, much like other user tables, and that it can leverage the resources of multiple nodes in the cluster?
Exactly. So it lives on the servers. It's a system table that basically is sharded like any other user table.
Great. I'm going to just keep a check on if there are any other questions. I don't believe we have any other questions. And but we'd like to welcome people to, continue this discussion on the YB users Slack community channel if there are further questions, where there are many people that can help. But otherwise, thank you very much for attending. Thanks a lot, Rahul, for presenting cross-cluster replication topic. And if you wanted to wrap up by saying anything, go for it.
Oh, yeah, thank you, Kannan, for hosting. And please join us in Slack and start us on GitHub. And was a lot of fun talking about cross-cluster. Thank you.